Uh, First of all, I'm Giacomo. I work at Guild. Previously, I was working at Amazon, and before that at ASDEV. I started using Docker at work in end of June. I was excited by Docker by the first day because I was using LXC before when I was at ASDEV, and it's really great thing. So I decided to talk about Docker because it's really a thing people should use, in my opinion. So first of all, what's wrong with your development environment? Nothing in particular, at least. Let's say that it's not broken. Everyone has his own workflow. Every company has his own workflow. So things are not that bad, to be honest. So let's fix it. The idea is to streamline the development environment, making it faster and easier to work with and to do things like an improvement. It's not really total things. What's wrong is that your development environment probably is more like a snowflake. By snowflake, I mean that it's particular, unique, and sometimes it happens that things work on my desktop, doesn't work on my laptop, doesn't work on my coworker laptop, because maybe I have a different version of the operating system or whatnot. Maybe some library we use, libxml is one of those, the graphic libraries as well. Sometimes it happens that minor variation in the environment can make tests fail or behave differently. So the idea here is to standardize as much as possible the development environment so that we are on the same page when we run things on it. First of all, what's Docker? Docker is an open source platform. It was open source from the first day. It actually was split from the .cloud platform. .cloud was the company behind Docker in the beginning. Now they did the pivot on Docker itself, so they call Docker Inc. now. And .cloud was similar to Heroku by many aspects. Docker is composed by different parts. One is the Docker engine. It's the container management runtime, so the guy is actually running the containers. I will get on what's a container later. Is a set of tools to package and share images, Docker images. We will get to that. And then there is the Docker app, which is much like GitHub, but for Docker images. So it's the platform where we share the images. The big thing about Docker is that everybody agrees on it. A lot of people is using Docker, a lot of people are publishing images, there is a lot of code reuse and share. It seems to me to see Ruby gems all over again, but on steroid. So containers. Containers is a form of operating system level. Virtualization is not a real virtualization method. Containers are not VMs. Don't think about containers as VM because they are not. However, the containers runs basically a single kernel, a single Linux kernel on the machine is shared between all the containers. Each containers can be seen as a isolated Linux system. There's no init in the container, at least shouldn't be. You can think of them like chroot, but with chroot even for network and source isolation, limiting, prioritization. On the lower level, it all boils down to C groups and namespaces, which are two features of the recently enough features of the Linux kernel. You can do resource accounting, is really good for monitoring, and that's it. It's basically most likely that it zones on FreeBSD or jails on FreeBSD, sorry, and zones on Solaris. The thing about this slide that containers are not VM, really. Images. So a Docker image is a actually is a set of layers packaged together. So each layers depends on the parent one, and all these layers are squashed up via an union file system. So the process running in the end sees a single file system, and it sees the file system as read-write, but it's actually not read-write, it's a read-only, and just the top layer is read-write. So what happens here is that you have a Debian image that had another image that had Emacs, another image that had Apache, and then you run your process inside the running from this image. It gets another layer gets created by Docker. It's read-write. Every time you write things goes into the layer. Since it's the top one, it masks everything down. So when you write, let's say you rewrite the Apache binary for some reason, it gets actually copied in the top layer. So it's copy and write mostly, but Docker can use different storage drivers in the bottom. One of which is AUFS, which is yet another union file system, or can use BTRFS, can use LVM device mapper to do this kind of trick, but it doesn't matter because it's transparent for us using Docker. So we like the system administration guy chooses one that is good for us, and we're set to go. By default, on Ubuntu, I think it uses AUFS. The really important thing here is that these images are read-only. Being read-only means that can be shared between multiple containers. So if you have like 10 containers running on Debian Wheezy, you don't need 10 images of it. You just need once, and the copy and write thing will do everything for you. And those images are shared between using the Docker app. So you push and pull images to the Docker app. All these images, you don't actually are not supposed to see what's written into the image. But each layer in this way forms a graph. It's acyclic, meaning that you don't have cycles into the graph. But basically each layer depends on a parent layer. So in the image there, the blue kind of boxes are those layers that are tagged. The one at the top is tagged blue is Debian Wheezy, and the bottom are Redis and Mongo. They both use the Debian Wheezy base image, and then they add more layers on their own, and they get tagged in the beginning. The thing is that Debian Wheezy is actually shared between Redis and Mongo. So when you pull from the Docker app, you pull the Mongo image and the Redis image. Debian Wheezy get downloaded just once because it's single machine, a single image that is shared between them. There's an example of some commands just to see how it feels. You can pull Ubuntu. Ubuntu is the repository in the Docker glossary, and 1404 is the tag. So you see we can pull Ubuntu 1404, Ubuntu 1204, Redis 2.8.13, Debian Wheezy, Mongo 2.6.4, and whatnot. And you have Docker images that actually showing the repository, the tag, the image D, which is a unique UUID, which is assigned to the image when it gets created. And I actually rebuilt the Redis thing. And the virtual size of the image. So you see the Redis image is particularly small, it's 98 megabytes in total. That's another way of looking at the tree. If you see on the third line, Debian Wheezy has a tag. So that image, which is 85 megabytes with that UID, is tagged Debian Wheezy. And if you see Redis and Mongo are like on the children of that image. So it's another way of looking at the other image. So, down to Ruby. Let's say we want to have an image with Ruby ready for us to be working on, and by default, Ubuntu 14.04 has Ruby 1.9, we want Ruby 2.1.2 because yes. And so we are going to write a Dockerfile to use Ruby 2 inside the Ubuntu machine. So there's actually the full Dockerfile for building the image. As you see on the first line, from Ubuntu 14.04, we are saying to Docker, look, we are going to base our image on 14.04. So when you build, it actually pulls the Ubuntu 14.04 from the Docker app at first. So I don't have to care on how to build a Ubuntu machine because it's already been built by someone else. And then the second line is maintainer is optional, but actually you are kind of supposed to put the thing there so we know who to blame when things doesn't work. And then there are 4 run commands actually doing stuff with Ubuntu. I won't get into the detail, but basically these 4 commands are installing Ubuntu, installing Ruby 2.1 by default on our image. Alas, that's the command for building the image. Docker build -d rubyday/ruby is actually creating an image in the repository rubyday. The image is called Ruby, so the repository is rubyday/ruby, and the tag is 2.1 because I'm building Ruby 2.1. So this is you run the command, do a bunch of stuff, and in the end you have a new image. Each directive in the Dockerfile adds a layer. That's why we saw Debian Wheezy and then a lot of layers, and then the one tagged Redis in the slide before. So the maintainer one is adding a new layer, and it doesn't grow the size because there's nothing actually being done there. It's just metadata. Then the first run command, which is sorry for this backend. The first run command here is it's adding the PPA, then we add the GPGK, then we do run apt-get update, and then we install Ruby. So 4 run commands, and we get out 4 layers. If you see the apt-get, which is not the last one, the one before, starting from the bottom, is adding 20 megabytes to the image because it's pulling data from the repositories and it's doing stuff. And then I install Ruby, it's another 36 megs, more or less. No, 33 something. So we can run Ruby inside our new container. Docker run -d, we see we want to run a command inside this container, and then we see Ruby -v, and it prints 2.1.2, which means that Ruby is by default Ruby 2, which is what we wanted. So can we remove these 20 megabytes? I mean, it's not a problem with 20 megabytes per se, but can we remove these apt-get update files? We don't need just adding 20 megas to our image. Yeah, we can do that. We can be clever. We can add another run command, which is actually removing the deb cache and the apt-get updates stuff we download from the net. We rebuild the machine, and let's see if it's working. No, it's not working because, as I told you before, each directive adds a new layer. So when you're actually removing the stuff from in the last run command, what it does, the copy and write removes the stuff from the top layer, but doesn't remove from the previous one because they have to be there because it can be shared by other machines. So the copy and write is actually not removing our stuff, and if you see, the size is still 257 megabytes, the same as the run before. So we actually did another step and we achieved nothing because of the copy and layer. There's a technique to avoid these sort of things, which is having a single run command with all the commands chained, and if you do like this, you can actually remove the stuff, and they actually get removed because the layer is committed when the command fails. But actually, this Dockerfile is the same as before. It's just grouped in a single image, in a single directive, but it's much more complicated. The one before was much nicer. That's a downside. If you look we rebuild the image and we look at the space, we see we have just 2 layers now. One is the maintainer, one is the single run. And the space uses actually 32 megabytes, which is what we have from Ruby per se. So we got rid of the file. So this works. Yay! Actually, I was cheating. The Dockerfile for Ruby is a bit longer because we need bundle and we need to be sure that we have Ruby 2 by default, and we want bit essential. Otherwise, bundle will fail when it goes to compile the C extension for our gems, and we want Ruby dev as well, the either files. Otherwise, it won't compile anything. So that's a bit more messy. If you see, I actually using 4 commands here, and the 2 commands at the top, the one that has the PPA and the GPGK, since they weren't adding space to the image, I've split it out in their own run system. So it's actually this image is actually comprised of 1, 2, 3, 4, 5 layers, and the 5th one is tagged as Ruby day /Ruby. So now we have a base image. Actually, this work was kind of for nothing because you can find a Ruby 2 image on the Docker Hub. You just go on the Docker Hub, there is already been done by someone else. But I wanted to show how to have Ruby 2 by default. At the same way, we are going to build a Dockerfile for a Ruby on Rails application. I download this one from GitHub somewhere. It's a to-do application, nothing fancy, uses SQL, uses Bootstrap and Angular and whatnot. It's just a standard Ruby on Rails application. It's really meant as an example, so it's nothing fancy, but you can find the code I actually added the Dockerfile and some other stuff on my GitHub there. And let's assume that we are using Postgres to develop this application because our production system has Postgres, so we don't want SQLite, we don't want MySQL, we just want to work on Postgres because that's what we are going to get in production. So we do want 2 containers, one with our Ruby on Rails application and one with Postgres, so that each member of our team works with the same version of Postgres and with the same environment using our Docker container we are going to build, so that everyone is based on Ubuntu, everyone is using the same image, so my machine, the application tests or the application itself is going to run inside the container, which is the same for everyone. So we have 2 containers now, and we have the problem that the first container, the application container, needs to connect to the Postgres container. That's right. It's like on a development machine, usually you use localhost, but localhost for the container is the container itself, and the other container is running somewhere else. How do we connect them together? That's the problem. In Docker, we do that using linking, which is a feature of Docker itself. Basically, you can link 2 containers together, and Docker is exposing some environment variable. When you link a container to another, and Docker starts the container that is linked to the other one, is actually injecting some environment variable into the container, so you can get like the IP address and the port of the other container. You can connect to it. So we have to do we have to basically play with the database underscore URL environment variable of Ruby on Rails to do the linking and connect to the database. That's the Dockerfile. We are going to go in back on it. That's an overview of how long it is. It's actually 10 commands. It's not that complex. And it builds the application and runs things. So let's go in depth in it. That's the standard stuff. We are, the first one is from rubyday/ruby 2.1, which is the image we built before. So we are telling Docker, I've built an image for this project. I'm using the image that I've built before. So if I have like 10 projects, I can reuse the same image all over again, and I don't have to mess with Ruby 2 once I've done that. And I'm the maintainer of this stuff. Then we add a user because we don't want to run our application as root. Does it make sense? So this add user is actually adding the user on the container. Then we run an apt-get update and we install some dependencies we need for bundle, which is libpq dev for Postgres gem, and Node.js because one gem was using exec.js and needed Node for some reason. And we are removing the stuff as we did before. So this command is actually doing the update, installing the packages, and removing the update file and the that we downloaded to get rid of some stuff we don't need. Then this block is actually the most interesting one. What we are doing here is the add directive is getting a file from the local directory and copying the file to the container to the specified path. So it's actually looking for a gem file on the local directory on the machine you are running the Docker build. So on my development laptop, on my directory, is taking the file and is copying the file in /apt/todo, which was the home of the directory of the user, inside the container. At the same way, we copy over the gem file .lock for bundle in the same location. And since the add directive is run as root inside the container, we have to change the permission to be todo, which is the user we want to use. And then we run bundle, and that's actually a simple bundle command. We are creating /apt/todo/bundle. We do bundle install, and we say that we want to install gem in that directory we have created, and we are running the stuff as user to do. So after the run command, what we have is that all gem that the application needs are installed by bundle inside the /apt/todo/bundle path. Everything clear so far? Yeah?
Choose the run, the two run lines.
Root. That's why I have -has, bean bes, and dash. That's why I use su, because I want to run bundle as the yeah, every run. So that's right. Every run directive is run as root inside the container, and the same for add. Then we say to Docker, look, every other command we are going to run, it's going to be run on /apt/todo. The work directive is basically, it's like doing cd every time we want to run a command. Then we say to Docker, look, we are going to expose a port. Expose is used during linking. We are telling Docker, we have a port, which is port 3000, which is the default for Ruby on Rails server. We are going to expose this port. So if any container wants to link to us, we are exposing the port. That's a way of telling Docker, we have a port we want to make available to other services to use. Then we add the code of the application to the /apt/todo. And again, since add is running as root, we change the owner to the user. If you look here, we already added the gem file and the gem file.lock. And now we are adding them again because it's copying all the directory and recursively, so we are actually copying the gem file again. And this is done for one reason. Let's finish with the Dockerfile. So basically, that's the end of the Dockerfile. These three more directives is user to do means every command we run by default, this is going to run as user to do. So after this line, if we have another run command, it won't be run by root, but it will be run by the user to do. And then entry point and command are two directives to tell which is the command that is run by default by Docker. So GMD, it says if the user provides no command, run bundle exec create server. And entry point means every time you run a command, even the default one, actually run through this wrapper here. So the final command, if you don't specify any command on the command line, will be bin bash opt to do bin docker entry point bundle exec create server. Okay, so the entry point is different between the difference between entry point and command is that command get replaces a default command that actually is run if you don't specify any command in the command line. The entry point is run every time. Okay, we need the entry point because we are going to mess with the environment variable to do the linking. So we need Postgres. We don't want to build Postgres. Let's say we don't know nothing about Postgres and what's the best way of creating a Postgres image. We pulled the image from the Docker Hub because someone already built the image for us. We want the version 9.3 because we want to know which version we are running from. 9.3 is the last one. Actually, it will be preferred to specify the minor version as well. So Postgres 9.3.5, which is the most specific version. That's up to you. You can say Postgres-latest to get the latest image, but I don't. I prefer to be explicit, and then say I want to run on Postgres 9.3. And then we run the Postgres container. If you see Docker run -d means that it's detached and run as a daemon. We give this container, new container a name. It's called Postgres, and we want to run the image -d Postgres colon 9.3. We don't specify any command after that, so it's running whatever it's been written into the GMD directive inside the Dockerfile for that container. I don't care. The Postgres guys took care of it for me. If we run Docker PS, which is similar to PS Linux machine, you get the container ID, which is, if you see, is a shorter version of the previous one. The image we are running, which port is exposing. So inside the Docker file for that container should be somewhere expose 5432. And the name is Postgres because it's the one I specified on the command line. That's it. So it's running, it's there. Now we just need to connect to Postgres. If I do an inspect, there is a command called inspect which returns a JSON file with all the settings about the running container. And I inspect Postgres, which is the name we gave to the container, and grep for network settings. I get these settings here. So we have the IP address, we have the ports that is exposing, we have the net mask and whatnot. Obviously, these things here are specific to my machine and this execution. So I can just get the IP address and write the IP address inside the application because it's not going to work if I move this thing all over to another laptop, or if I'm going to run this tomorrow. Not going to work, I can just start code. It's not going to work. So we have to find a way of actually getting these things like in a dynamic way. Ouch! So sorry for the color. It was different on my skin. But anyway, that's the entry point bash script. So briefly, what it's going to get, it's getting the Docker environment variable It's creating the database URL variable for RAIDs. If you're familiar with RAIDs, I think you do, you can expose the database URL using an environment variable instead of the config file. So we are saying, hey, look, RAIDs, connect to Postgres using that user, that address, that port, and that DB name, and this DB name we are getting those from Docker. If you see, is DB underscore port underscore 5432 underscore TCP underscore ADDR, and the port is the same underscore port. It's quite long, it's quite messy. It's the way Docker used to expose the environment variables. So these variables are set by Docker before the execution of the entry point. And that's a standard way of naming things in Docker. You will get used to it if you use Docker. And actually they are populated by that number we saw before. But Docker is taking care of it. I'm not using I'm not coding any kind of IP address or port. I'm just using the environment variable. Then we execute whatever the user passes on the command line. So bundle exec create server. And when we do that, we have the environment variable for the command. If I try to execute this thing by itself, it will boil out and say, hey, unbound variable, because no one is setting that variable that I'm expecting to get, because I'm not telling Docker here to link to the Postgres container. If you see on the command line, there's nothing telling it to link to the Postgres database. So that's actually a feature. If we do, however, link using --link Postgres, which is the name of the container, and DB, which is the alias I'm going to use into this run, and I'm running env, which is printing out all the environment variables. If you see, we get like a bunch of environment variables that are injected by Docker. The last one is the one that we set into the entry point. So it's actually getting the previous variables, meshing all around, and setting the database URL, which is what we wanted to use in the first place. So it seems to be working. If you see the alias, which is the column DB, into the --link parameter, the alias is used to populate the prefix for all the environment variable. So Postgres column DB, all the variables are prefixed by DB underscore. So if I say like Postgres database, it will be database underscore m underscore pgdata database underscore whatever or not. So the alias is set chosen by you. And at this point, it's pretty much standard business. We have the container for the application built. We have the container for Postgres. We know how to link them together. We wrote the entry file. We know how to discover the IP address and the port of the database. And we can run stuff inside the container. The first thing we run is the rake db create task. So we want to create it in the database because obviously the Postgres container doesn't have any database at the beginning. Then we are loading the schema so that we now have a database and it's actually populated with what we expect in the application. And then we run our container using link because we need to have these environment variables populated. We are giving a name which is to do up. We are exposing a port. So -p 3000 column 3000 means, hey, Docker, I want a port forward from my machine to the container. So when I connect to localhost on my development machine on the port 3000, I end up into the container. So I'm actually seeing Ruby on Rails. And then -d means demonize, detach, so it goes on the background and then I have to keep a shell open. And that's the image that I want to run. I'm not specifying any command after that because by default I'm going to run bundle exec RAID server, which is the RAID server. If I do a Docker PS, you see the important part are the names and the ports. If you see on the first line, it's actually telling us I'm doing a redirect from 0000, which means any address, 3000 to the port 3000 inside the container. And the Postgres container has two names now. One is Postgres, which is the one that I choose when I started the container before. And the other one is todo-up/db. That means it's aliased as db for the application todo-up and link it together. That's the way Docker is telling us that these two containers are linked. If we do a net stat on our machine, we see there is a process called Docker proxy, which is running on port 3000, which is doing the port forward. And if I try to connect with CURL, I get HTTP 200, means that the application is responding and is working. Yeah. So it works. That's a bit too much work. I mean, I don't want to go through these all this time. So the good part about this is that now you have a to-do image. I can push on the Docker app. You can pull rubyday/to-do app from the Docker app, and you're ready to go. You don't have to care about details. You don't have to care about how the Dockerfile is constructed, like I did with the Postgres. You can just start it, but you still have to run the Postgres container, run the application container using the -- link with the proper alias, otherwise it won't work. So there's a bit of knowledge you have to have before running these two containers together. Enters Fig. Fig is a tool which was recently, I think the company behind Fig, probably mistake, whatever. Fig is a tool written in Python actually, which is really simple in what it does, not simple in how it's built. Basically, you write a YAML file, which you commit into the source for the application itself. And the YAML file basically tells how to construct all these. Let's say now I have two containers, but we probably have like 10 each container running its own service. So it's much easier. If you look, the web container is building from this home directory. So we have the Docker file, and we have the gem file, and we have whatever we need. We want to link to the B container, and we're exposing the port 3000 doing the port forward. And the B container is running on the image Postgres 9.3 and exposes a port which is 5432. Okay? So basically with this thing we are describing all the container we need. So once we distribute this Fig YAML file, the other developer just use Fig and don't care about how the names must be done or whatever we need. Basically it's going to automate a bunch of commands for us. We have to change a bit the entry point because Fig is using a different naming for the environment variable. Instead of db underscore, it's injecting db underscore 1 underscore because you can have like 10 version of the same container, but that's a technicality. Don't worry too much about it. So we run Fig up and -d, which means running the touch mode, and it's going to create the Postgres container, create our web container, do the linking, and run the command. That's all a new developer should need when he starts to work on the application. It will build the image and do whatever it needs. And then we run fig run web bundle exec create db-create, which is the same command as before, without the image name, without the linking stuff, without all the command we gave on the command line. It's much simpler. Fig run, which container, which command. That's easy. And then we creating the schema. Again, netstat showing Docker proxy working, and we try to access the application is actually working. So much faster. You write the Fig YAML file once you push it into the source code alongside with the Dockerfile, alongside with the gem file. So altogether they build the image and they know how to link everything together. There's a couple of more of Fig commands people could use. So PS is one, is actually showing the container that are running. To do db1 is the name that Fig choose for my container. To do is the name of the directory in which I'm in, actually. So my directory was /to-do. Because db is the alias that we made, and _1 is because it's the first one. Because Fig supports scaling, so you can actually use, if you remove the port forward, you can actually use Fig scale web 2, and it's stuck in 2 containers of the web one. And if you see the last command, you have a Postgres database with 2 RAID server that you can do scale up and scale down. It's not useful in development mode. You really care about having 2. And if you see there, it's actually choosing itself the port, a random port for doing the scaling, because if you can't be 2 people on the same port, so you have to remove the port forward. Fig is really has a bunch more commands like build, like just go get and explore it. It's really handy. It's meant to share the knowledge that it's not inside the Dockerfile. So let's say we work together, I wrote the Dockerfile, I published the image, and then you still need to know how the alias should be named and how the container should be linked and what are the names of the environment variables. With Fig, you mask everything. You just have Fig and run Fig. It takes care of everything. And most importantly, you have inside the fig.yaml all the information you need to reconstruct the environment. That's pretty much what I wanted to show. I got a couple of tips. Learned mostly the hard way. Leverage the cache. So if you remember, we add the gem file into the Dockerfile. We added the gem file, added the gem file.lock, then we added again all the files into the local directory. That's why, because when you change something at a certain point in the Dockerfile, it has to rebuild all the way down. So if you change a file inside the current directory, like do a touch of a file, it sees the file has changed, and when it goes to the add command, it can't use the cache because the files have changed. So what it does is redoing the add and redoing everything back down, because every command, every directive below the add is going to use the cached layer. So if I swap things around and I try to rebuild, instead of using like the cache and took like 2 seconds, it's going to take 2 minutes because it has to go through bundle install again, which is the slow part. So learn how to leverage the cache. It's something you figure out while working on Docker, how to, the order of in the Dockerfile really matters because of this cache. So try to be clever and reuse the cache as much as possible. So do add dot when you add the files for your application. The lower in the Dockerfile, the better, because there's less layer depending on it. Especially if you can do bundle before adding the files, it's really great, because you don't want to go through bundle install from scratch every time. Really, you don't want to. Storage driver, I was mentioning it before. The device mapper is slow in creating containers, it's slow in removing containers, it's actually slow. AUFS works better for now. Unfortunately, it's only on Ubuntu. Means that you have to run Ubuntu on the machine that is actually hosting the Docker daemon. BTRFS is another option, is kind of the future, if it will ever work, maybe sometimes. But anyway, be aware that you have to choose the cache, because once you start creating containers, you can't swap out the storage driver, so give it a thought before actually start working with Docker. I think with the recent packages in Ubuntu, you have to select AUFS, otherwise by default it's going to use device mapper. And kind of, if you are on CentOS you are kind of forced to using device mapper, but I found like a UFS to be much faster in creating containers. Always tag your image. Don't rely on latest. It's like using head for tagging in Git. So tag your image, give it a meaningful tag. That's you can reuse the tags from the Git log. So you can always tag the image with the Git tag with some shell scripting. When you pull, especially from, always specify a tag, because I was using Postgres 9.3. What happens tomorrow if I pull latest? I get 9.4 beta 2. I don't want to test my application against the beta. I want to maybe generally speaking, I don't want to test against the latest image, because tomorrow I get a new machine, I pull the Postgres latest and get 9.4, and my application is running on 9.3. So always be explicit and put the tag when you do the pull and the from. That's really, don't rely on latest. There's a way of actually running the container with a shell, doing stuff, and then doing a commit. It's the equivalent of creating a Dockerfile. You can do that. You will discover that like the first day you start working with Docker. Oh, I can run a bash, inside the container, do a apt-get manually, do stuff, and then commit to the container with a tag and I build the machine. Don't do that. Prefer Dockerfiles because they are you can reproduce the build system. It's actually self-documenting, so you know all the steps to go through the Dockerfile and get the image. If you run a bash, do some stuff, then you leave the company. Who knows, you run inside that, how to recreate the image. Or maybe just me in a week, I don't remember, I don't care. So use the Dockerfile. It's much like the difference between doing stuff manually and using Chef on a server in a different way. It's self-documenting at least. You know, I know you thought about it. Don't install SSH inside the container. So the question is, how do I get a bash or a shell inside the running container? Let's say you have the container running on production at a certain point because you discovered that Docker is cool. You want to connect to the container and look what's going on inside the container. Don't install SSH inside the container. The container is meant to be one process per container, so don't start 3 processes, don't do forking, don't do anything. There is this thing is called nsinit, which is a script to enter a namespace. The namespace is what's below the container, so you get a bash inside the running container without using SSH. You SSH inside the machine, and then you do nsinit to get a shell inside the container. That's how it should be done. Don't try. There are images somewhere, Fusion, the same from Passenger. They built an image with syslog, SSH, run it, and a bunch of other things. They are kind of really, they think that it's a good idea. The community is kind of split. The Docker developer are on the same page of running one single process in the container. It's much simpler, so if you can avoid, just do. One process for a container. Don't fork, don't double fork, don't do nasty stuff, don't try to demonize the self, just run in the foreground, leave to someone else how to deal with the foreground process. So don't do anything in particular, just the bare minimum. Stay in the foreground. Because you can use a process manager to actually manage the Docker containers running. You don't have to run in production, especially on staging, you don't have to run Docker run -d to detach the container. You can run in the foreground and then write an upstart or systemd script to actually manage the container. So when you do start my application, service start my application, it will run the upstart script that will run the container. The container will run in the foreground and upstart is managing it. The same with systemd. It's way better. Distribution, like it's working for ages. Don't reinvent the wheel, just exploit what's there. I think upstart and systemd is probably all the Linux distribution out there. If you use Debian, you can write and if you don't use upstart, you can write a syswinit or whatever they use. That's it. I think we have 10 minutes.